hard. A lot of work. Okay, you're in. Okay. Okay, good morning, guys. If I can have your attention, please. We have our friend here from Interstate, Jerry Boggs. He will introduce the rest of the team over here. As expected, we're going to talk about generators, a lot of stuff about generators. So I'm going to let Jerry walk you guys through different types and sizes of generators, and then we take a break. And then after that, he will walk you through the software to size generators. I know I walked you through this software. He's going to go kind of the next level a little bit, and you know, the conditions for generators and so forth. So go ahead, Jerry.
Good. Good morning. My name is Jerry Boggs, and I've been in the engine generator business most of my working career since about 1969. I have with me, I'm with Interstate Power Systems. We're part of Interstate Companies out of Minneapolis. We're located down by the Mega Mall. And I have two of my associates with me today. And Scott, why don't you stand up and introduce yourself?
Morning, I'm Scott Montague.
And Todd?
Todd Shabby. I've been with the company for about 3 years, but I figured I could learn a thing or two, so I decided I wanted to come with you.
So I am here mainly today for you folks. I give a lot of talks to consulting engineers, contractors, and I'm here for your benefit. So I'm very informal. If you have a question at any time, either ask it or get my attention and we'll talk about it, okay? Having said that, I will move on. This is our agenda today. Brief introduction, just did that. We're going to talk about the different product types that are out there for generator sets, common options and why you would want them. We'll also talk about the all different kinds of transfer switches and what they're used for. Different types of loads, and I'm sure you're well aware of different types of loads with everything I see on the walls here. And then anything specific to what you might be involved in here in some of your projects. I'll help you and guide you. I won't do it for you, but I'll help steer you in the right direction to find a solution. You have a copy of my business card, too, in your folders that I passed out along with the entire presentation. You're welcome to email me, give me questions at any time. If you're stuck, you want to learn something and you don't understand something, and I'm going out of here today, so follow up with me. I'll get back with you.
And Jerry, just to give you an idea, we are sizing a backup generator standby for a 10,000 square commercial building. The voltage system is 28120.
Okay.
And we're thinking of diesel, but you can suggest any other fuel.
Are you going to have IT on there, UPS?
Very limited.
Okay. Okay.
With an auto transfer switch where we can pick up the whole building.
Okay. We'll talk about that when we get into it a little bit.
Just to give you a reminder. Yeah.
Okay. Very good.
Yeah, hopefully you guys find some of that 5,000 square feet.
Yeah, and there's a future expansion for 5,000 square feet.
Good input. Okay. Very good. Let's move on. We'll have time for questions anytime. A little bit about our company. I'm going to sit here. You guys can still see me. And down. We've been in business down at Interstate since 1958. This slide is just a little bit dated. We've actually picked up a couple more states. We cover about 10 states now. We're all the way down as far as south as St. Louis, and as far west as Montana. So we have parts of Wisconsin as well, and parts of Illinois. So we're very solid in the Midwest. And this has changed a little bit. Again, we got to add a little bit of Missouri here. This is an old slide. If you go up and down the freeways, you'll see old I-State trucks on the freeway. That's also our company. We're basically split into two groups under Interstate Companies We have I-State trucks. We also have Interstate Power Systems, which our people here today are part of. And we're a part of the Power Systems group here. What we're going to be talking about today is what we see in the picture here. That set was in PowerGen a couple years ago. That's 3,250 kilowatts. It's a 20-cylinder V-block diesel engine. And it's about 4,500 horsepower. So it's big units. That's on the high end of our sets. We go down to 30 kilowatts. We carry the full product line. We have both diesel and gas. We have automatic transfer switches, primarily ASCO. We also sell GE, Zenith as well, but we can get any transfer switch, Russ Electric, and so on. Switch gear, we do paralleling switch gear. We will help customers design paralleling switch gear, whatever they need. And a full line of accessories to get in and out of any application. Our natural gas and LP units are primarily General Motors. The slide's a little bit dated in that we have 130 kilowatts through 400 kilowatts in a Doosan powered product on the gas side as well. And we'll probably see more units over the years come in under that gas side of the house. Again, the diesels are from 30 to 3250. Primarily Detroit, or MTU, which is the new name of Detroit Diesel, starting at about 200 kilowatts now, moving up through 3250. Below that, we use the John Deere product. Also within our product line is the Waukesha generator. This is not a standby product at all. I just wanted to show it one slide to you and let you know that this type of product exists. What it's for is primarily cogeneration markets. These are generators that are going to run all the time. So what you're going to see is sleeve liners and things like that. A lot heavier duty engine. Very rebuildable. You can build these things over and over and over again. So they tend to be a lot more expensive than a standby product, but they're designed to run all the time. Take heat off the engines to use in processes. I sold one of these most recently down in the city of Rochester. Uses this, and they take the gas off the wastewater treatment plant, the methane gas, clean it, and run it through and power the engine with it. So they have a cheap fuel source, and they take the output of the generator portion of that, and they run the plant in Rochester. And also they take the heat off. They take the heat off the exhaust of the thing and off the water jacket. And they use that for part of their process. So it's called cogeneration in its truest sense. So they're using that.
How long can they run?
Typically these things will run around the clock. As long as there's a fuel source. Typically what they'll do is if there's a time of year where you can't run with the digester gas, they have a natural gas backup that you can use if you still want to run the generator set. So there's systems like that in place, but it's designed to run as long as you need it. Okay, any other questions? All right, we're going to move into discussion on the generator sets. There's another picture of that big beast that I showed you in the other shot, what it looks like on the trailer. Look at how high that radiator is against that semi front end that has the extension on top of the cab. This is a big set. Here's one that's being delivered right here in Minneapolis. This went down to a data center. Again, just an idea of the size of these things. It's on a double drop 40-foot trailer being delivered. Here's a data center that is here in St. Paul. They didn't want to tell who it was and where it was, but these are very secret locations typically because of the sensitive nature of what they do. Data is a very strong thing to guard these days. Here, you'll see on the data center, getting back to your question here, how long does this run? These sets are also designed to run for a long period of time. This is a day tank here, and there's actually a third unit, so there's another day tank. There's a very large on-site fuel source here. You'll notice that over here on the generator set, hey, we've got a set of oil filters here, a set of oil filters here, we've got a set of fuel filters here, and another set of fuel filters here. That's a backup to a backup. Again, these are mission critical sets. They don't want them to go down, period. So they have many, many backups in place. That's just a couple of very common ones. We'll see some other shots. There's the fuel filters here again, and the oil filters, 2 sets. So what they do, if they're going to run for a long, if say we're in a homeland security situation, we're going to be running for a long time for whatever reason. These things you can change the oil filters on the fly. You can switch to this set of filters, change this set, clean them up, switch it back, and then change these. So that's the idea here. We don't have to shut down, period. And multiple sets. Again, if you have a problem with one set, you typically would size an application like this to allow for one set failure or maintenance, scheduled maintenance. Here's a unit. A lot of people use these. You've seen Target stores every day. A lot of them have a backup. This is a super Target. This one's up in Blaine, in your neck of the woods. Another shot. This is another installation using a different type of enclosure. We'll go through enclosures in a second here. Controls. All the diesel sets have controls. Here's kind of the old workhorse. Down here we have the AC portion here, voltage, frequency, that kind of thing for the set, and amperes current. Down here at the bottom we have a full set of engine gauges and maybe a time clock on the end there, hour meter. Sonic alarm here is if there's, we've got a monitor system that's NFPA 110 compliant. A lot of these sets have to meet the NFPA 110 standards. So the control will alarm if there's a problem that it sees, high water temperature. For whatever reason, the temperature on the engine is going up. Oil pressure is dropping. Maybe we got a leak someplace. That's what the NFPA controls are all about. We have a digital controller also. This is more state-of-the-art. As we move through time, everything is becoming digital. So this is the MTU DGC 2020 control. Again, fully compliant with NFPA 110. It's a little more functional, a little more agreeable. It's got terminals, RTU ports that you can get into an RS-485 connection. So you can monitor it, or an RS-485 out to a remote annunciator. It might put up in a hospital location, for instance. That installation we saw at the data center, that might be in a room that's in the basement, but we want to monitor it from up in another location. It works with the remote annunciator, which is this device. Primarily, it's going to tell you what the problem is on it, and that sonic alarm in the middle there is going to start squawking at about 98 dB. Hopefully nobody's sitting too close.
That'd be long.
Yeah. All right. Covers a little bit on the controls. Different fuel types that we deal with on generator sets. Pros and cons. I've used this slide for years and years, but the pros and cons are still the same. Natural gas. What's good about natural gas? No storage issues. It's lighter than air, so if there's ever a leak, it's going to go up. That's a good thing. It's a readily available source. It's clean burning, and it can have an automatic propane backup. When I was in California earlier in my career, earthquake zones were a very big concern. So natural gas lines could be interrupted in an earthquake, so that's the reason for an automatic propane backup as well. Another thing that it's kind of hidden there, it's under no storage issues. We don't have a tank. It's a city supplied source, so that's kind of a big plus in a lot of applications. On the negative side for natural gas, it's a lower BTU fuel. In a lot of cases, you're going to be derating that gas engine a little bit. Typically 1,000 BTU per cubic foot for the energy content. And like I mentioned, for the earthquake zone, service interruption is possible since you are on a city supplied source. Propane. Again, on the positive side, it's a clean burning fuel, very clean. It stores well, typically in the big propane tanks outside. It's available on demand. It's got a higher BTU content than natural gas. It's 2.5 times more energy in a cubic foot of that fuel. It's typically 2,500 BTU. And it can be taken off as a liquid or a gas. Here's a sketch I did on a tank. Think about Minnesota here. It gets very, very cold. North Dakota, we had this problem last year. We had a generator set that was up on a hill, right off the freeway, in a blizzard, and it was cold. What happened was they had a tank outside. They had the generator inside, and they said, this thing just won't run. And what happened was this tank shows the liquid propane down here. The ambient temperature was so cold that it couldn't vaporize enough fuel to run the engine generator. So that was a vapor takeoff. So the fix for that is you can go to a liquid takeoff, which you actually have a suction tube which goes down into the liquid propane, comes off, and it runs through a vaporizer. And typically they run the vaporizer right off the jacket heater. You've got anybody know what a heat exchanger is? They got a primary loop with engine coolant running through a heat exchanger, and that heat from the engine coolant is enough heat to generate into the secondary a vapor. They run the fuel, the liquid, through that side, and it vaporizes in that vaporizer. And then the vapor is fed into the engine. So it's basically still running on vapor, but it's a liquid takeoff. The negatives for propane. Again, I've been at this for a long, long time. When I was in the Pacific Northwest, we had a lot of radio repeaters up on the tops of mountains. And these radio repeaters would have generators in them. Typically, they were unmanned. Propane is heavier than air, and it'll settle in low areas. And these were telephone companies that had these radio repeaters on the top. A lot of them back in those days, because this was back in the 70s, had a lot of relay contacts. What happened in one instance was we had a radio repeater that was blown off the top of the mountain. We had a propane leak, got in, it settled in, again, it's heavier than air, so it went down. All it took was one relay contact spark, and then the rest was history. So, very dangerous with propane inside the building. Liquid takeoff requires more equipment. That's another negative, because we've got the vaporizer that I told you about. So, that's the cons for propane. Typical systems look like this. These are engine-mounted components here. Typically, we'll have the carburetor here, a secondary regulator, which knocks it down to a low pressure for the engine. Solenoid valve, so when you get the signal to start, this valve will open and allow the fuel to come in. Out here, we have the primary regulator, typically like in our house and every commercial building. The most typical is like a 2 psi inlet to a primary regulator. On the outlet side, we're at about 7 to 11 inches of water. and that's brought into the primary side of the secondary, and it drops down to about 4 to 6 ounces going into the carburetor. And out here we have a little dry fuel strainer, which is ahead of the primary fuel regulator, and a manual shutoff valve. Propane is very similar, but you're going to be coming from a tank. Diesel. The pros for the diesel system is probably the highest BTU fuel content available from us. Low volatility, slippery, but it's not explosive. And it's readily available from a lot of suppliers. Even in cold weather like Minnesota, North Dakota, these areas of the country, different refineries around the area, coke refineries down in Coates, make additives that allow higher cetane ratings mainly for diesel systems, and it's kind of an anti-gelling agent as well. So there's a lot of additives that we put in to keep the trucks running and so on in the cold weather that we have, and our generators. On the negative side for diesel, storage requires some maintenance. If you don't use it enough, if you size too big a tank for your application, and you haven't used enough fuel, you might get stuff growing in there after a while. So a good reason to kind of optimize the size of your fuel tank. Typically, just from a design standpoint, so you know, we size either 12 hours full load or 24 hours full load most often for generator sets. And because we've got an EPA department in our government, we actually have a tank within a tank. So dual containment. So a long time ago, how that all came about was we used to, like back in my days in Oregon, I planted a bunch of fuel tanks up on these mountains, and they were single wall tanks. Well, we didn't know at the time, and electrolysis in the soil actually started acting on those tanks. And after 20 or 30 years, they would start to leak. So that's a negative thing as far as the environment is concerned. And that's how dual containment got born. And a lot of mom and pops got taken out of the gas station business because they had to go back and dig up their tanks and replace them with dual containment systems. Very expensive to fix, but that's the EPA. Cold weather, again, I mentioned a little bit about that. We may have to require some more additives for cetane rating. And light loading, if you run it lightly loaded, you're going to have issues on the generator set. Again, back in the Northwest, Pacific Bell brought me up to a job site one day. They were all excited. Terry, we got this generator. We got a great deal on it. But it's got a problem. Can you look at it while you're up there? I said, yeah, let's go up there. So we drive up to this mountaintop site, and they got this old generator set. It's huge. And they said, we got such a good deal on this, but what's all of this stuff? And the whole side of it had black juice dripping down the side. I just took one look, and I said, hey, you're running this thing without a load, or a light load. Well, yeah, but we got a good deal. I said, well, what's happening is they weren't burning enough fuel. Diesels are designed to run under a load. Unlike cars that have gaskets and stuff, diesels have some areas of their surfaces where they machine them very tight, and there's not a gasket. And you'll see that in the exhaust manifold is a good indication. And what happens, if you don't get that engine up to temperature to where the coefficients of expansion fully seal that surface, the fuel that you don't burn will drip down the side of the block. So there is a cheap fix for it, but they have to get some load on the unit and run it for a while, and that'll burn that unburned fuel out. So light loading may require more maintenance, and that's in the form of a late load bank. Since this was a mountaintop site, they said, what can we do? I said, you need to have a bigger load on this thing. So they didn't have money for a load bank. Load banks can be kind of expensive. So I sold them an electric furnace, and that took care of their problem. It's electric furnace is the same as a cheap load bank. So anytime that unit ran, that furnace would also run. We just put it outside. So it's always a way to get around it. Go ahead.
My question is going to be 3 in 1. You talked about natural gas, propane, and diesel.
Uh-huh.
From your experience, which one is cheaper to run? Then which one is cheaper to maintain? And which one do you recommend for the customers most?
Well, that's a good question. It's going to be more than just the cost of the fuel source. It comes back into set economics and also the size that you need for the set. Typically, the most cost-effective is going to be natural gas. Again, the trade-offs are going to be, say you need 100 kW set. It might be good for some applications, buildings that don't want to mess with fuel storage and stuff. It's going to be cost-effective. Diesels are going to be more cost-effective once you get, say, above around 100 kilowatts set. Then diesels actually get cheaper than natural gas. And that's strictly a function of how many sets are manufactured. Natural gas are basically a gasified automotive engine that's been industrialized. They put governors on them and stuff like that. So it's an engine that's readily available. When you get above 100 kilowatts, it's more likely that you're going to see diesels, trucks, light trucks. So we have more of that base available. So it's more a factor, not so much, somebody wants a natural gas set. No deck, mutual insurance out in Fargo, North Dakota called me. We want a price because we want to know what's cheaper for a natural gas. Okay, I can do it, but at that kilowatt size, 400 kilowatts, it's about twice as much, just regardless of emissions that we're faced with today, which we'll get into later. If we were 2 years ago, a 400 kW is going to be 2 to 3 times more expensive than a diesel. So it becomes economics as well. Does that answer your question? Okay, enclosures. MTU offers, and most manufacturers, not just us, but all manufacturers offer different grades of enclosures. This is a pretty standard grade. The one thing here that's kind of neat about it is the muffler's inside the enclosure. That's a little rain cap that's sitting on the exhaust outlet there. That's designed to keep birds out. They will go in, as will critters. So that's and we have an inlet maybe on this side and an outlet over here. And one thing I should tell you about a generator set, any generator set, it's not like your car. You've got a radiator and a fan, but they're not the same. On a car, you've got a sucker type fan to where it comes in through the radiator in the front typically. It goes, and the cooling air moves over the engine and goes down by the firewall, right? Generator sets just sit there. So what they have is a pusher type fan. And in a situation like this housing that we have here, we'll say the radiator is sitting right in this area here. It's going to push air out this way, which is going to create a negative pressure within the enclosure and draw air in through this side. So a little different technology, same stuff, but instead of sucking the air in, it's pushing it out. Another style, this is basically we could call this a semi-sound attenuated unit. Here we have the muffler on top, so it's just a little different design, and it's nice to get the exhaust pointed up and put a rain cap on it. Down in the bottom, I'm going to point out a couple other things here. And we're going to talk about noise in a little while here, but while I'm here, I'm going to show you. Remember I said this is a pusher type fan. So it's pushing the air out here, and the scoop is going to direct that air up. This is a form of noise attenuation. In other words, we're going to make this set a little quieter because noise travels in a straight line. If I didn't have this scoop on there, that radiator would be right there, and it'd be kind of noisy because it's going to come right out of there. It's in a straight line. So we direct that air up, and that's a form of attenuation. And because we don't want rain and stuff, we put slots down here in the bottom of this scoop, so anytime it rains, you know, or gets snow in there, it can drain out the bottom. So down here, this black part, that's a dual containment tank, fuel tank. This is a diesel set, obviously. And that's the tank within a tank sitting right underneath the generator set. So, and this little piece there is a step because we want to be able, the NFPA and the NEC says, hey, this can't be more than, we got to be able to get to the control. So we put a step on the tank to make sure that you're able to reach that. Just a little additional part of the design. This tank isn't quite as high. And again, this is also a form of sound attenuation. What you see here, little different design. We've got a smaller tank, so we don't need our step. This is probably a 12-hour tank. Up here, these are the inlet louvers. Remember I said when we have the fan over here pushing, there's actually an up scoop inside of this piece of sheet metal right here. So we've got exhaust air moving up. We're turning the air on the inlets here. Again, we're turning it twice, so we have no means of getting noise directly out of the box. So this is a form of sound attenuation. Here's another sound attenuation design. This one, I think this is at Northtown Mall. Anyway, you see two scoops. This isn't raisins, but we've got an inlet scoop on this end, and the air here, because of the negative pressure, the radiator fan is obviously on this side then, right? Pushing the air out and up. So that takes care of the noise on that side. Here we're turning the air, it's coming in, that creates the negative pressure, this fan here, by pushing it up. So we've got negative pressure inside the enclosure, pulling air in through the inlet, which is here. We're turning it and bringing it in. Again, you can't get straight out through those inlets, so that's sound attenuating there, and we're sound attenuating by pushing it up on the outlet. And again, the dual containment tank sitting below it. There's another design using sound attenuation. This one is definitely at Northtown Mall. We put everything in a box and make it look pretty. There's an internal silencer. We've got sound attenuators, which are actually elongated pieces stacked on top of each other. Just a different form of attenuating the noise. And we have those on each end, both on the inlet and the outlet. So this is also a very quiet design. And again, it's probably a 12-hour tank due to the height. I think this one's like a 1,500 kilowatt set. This one's at a hospital in Hutchinson. Same kind of thing. It's a sound attenuated enclosure with the base tank. Very common. Also, we have trailer mounted sets. This is a set I built for the city of Edina with a Kohler generator set. What cities like doing is they have different voltages at a lot of different places. So they'll put on a big switch. So we can switch, we take a 12-lead alternator, the generator end, and we'll switch between the outlet leads in different configurations and make different voltages. And we can plug in certain lift stations. They might have a well that they need to back up, or they might have lift stations, so they might have different voltages on these different plugs. And I've got breakers up here for the different voltages when we switch to them. The generator set control I've located over here on the side, just to make it easier for the operator to run all of this stuff. So that's a way we do it. Water jacket heaters, different types.
Before you leave, you talked a lot about the enclosures. I don't know if you just want to say a few things why the enclosure is so important in the design. I don't know if the students understand You talk a lot of stuff about enclosure. Just a few words about why the enclosure is a big deal in the design.
Okay.
You know, just in the one, you know.
Enclosures are very important because we have to keep that engine warm. Part of NEC and NFPA is a requirement that emergency generators start and be online supplying power within 10 seconds. To do that, we put a water jacket heater on the unit, but we also typically will, especially in our area, we'll put insulation, foam, motorized louvers, all designed to what? Keep the heat in the enclosure while it's not running. Okay? So the insulation in the enclosure is important. Water jacket heaters are important, all leading to that 10-second start and supplying load capability.
And the noise too.
And the
Also.
noise, yes. Okay, and water jacket heaters on a big V block like I showed you in the pictures, that one in the truck and in the trade show. You're going to have a jacket heater like this on each side, each bank of the cylinders. Smaller ones will get a little tank heater like this. You can probably see and buy one of these for your car. Little Kim hot start heater. Battery chargers. Interstate has gone to the to this brand. This is a Sense charger that they make for us. This particular model is called the InterGenius. And the reason we like them, you see the flanges at the top here for mounting and so on, and the digital control. What used to happen in the old days for generator sets is the battery chargers had the old analog meters on them, and you'd get to the job site and the needles would be laying in the bottom of the meters because it vibrated so much. So we couldn't really put them on the sets. These are a lot more durable, and we will mount them on the sets. Vibration isolation, all different kinds. Just a slide to throw in and let you take a look at the different types of isolators that are out there. They make isolators. This is a common one here that can be modified, and the modification looks like this guy over here, and this is designed for earthquake zones. These little pieces on the side over here are called snubbers, and they are for lateral movement rather than vertical. Little cheapy things that we use all over the place are neoprene cork combinations here. We call it waffle pad. We use this type here for integral isolation where we don't use springs. These springs are used primarily on big sets where the skid is solidly mounted to the generator and engine and the alternator. And so to isolate the vibration from the pad, then we need an external isolator like this. So the bigger sets get typically the springs. In the smaller ones, 200, 100 kW, that kind of thing, a lot of times, we've even got them now up through 600 kW, where we put this type of isolation between the generator set and the skid. So you can bolt it all the way down to the floor without any problems for maintenance and stuff, and critters that might get in there. Okay, that covers generator sets for what I have right now. Do you have any other questions on anything that I've covered so far before we move into transfer switches? Okay. A transfer switch, its job, I came up with this definition 10 years ago. It's a device used to safely transfer power to the load between two different sources. You think about it, power fails. A lot of quote-unquote handymen might think, well, I can get this fixed. I'm just going to go grab me a little portable generator and plug it into an outlet and backfeed my electrical panel. I'll be able to run everything all over the house that way. Only one problem. If he doesn't open his main, or he doesn't have a main on his electrical panel, When the utility comes back, something's going to go bang. And he's going to have what we call a thermal event. So automatic transfer switches are designed to safely transfer power between two different load sources. And we're going to look at some one-lines and what I mean by that. First type is the most common is the open transition switch. It's most cost effective, but on the negative side, you will see a blink in the lights. Say, take for instance, power fails, generator starts, we get over on generators. Power fails, the lights are out, nothing I can do about that. We're on the generator set later, the lights are on, utility comes back, so that's on, but I still got to get to it. So an open transition means you're going to be in open circuit for just a little bit. And it's only about 100 milliseconds these days for most transfer switch manufacturers. But when it leaves the generator and goes back to the utility, it's going to be a little blink in the lights. It's kind of a negative for some loads. And here's what it looks like. Utility power, the normal operation, utility comes in here, moves through the contactor down to the building load. I'm going to tell you a little bit now about the 4 types of time delays that are in every type of transfer switch I'm going to talk about. I may have it shown a little later but I'll describe them now. There's 4 time delays that are typically in there. And again, if you think about a snow-covered day here in Minnesota, maybe a tree that's broken out there. It might be bumping on a power line down there. We have a time delay on start because a lot of these diesel sets have these huge starters on there. We don't want to be slamming that starter home every time that tree bounces the line and the power opens up for just a second. So they put a time delay on start, and it can be like 2 seconds. And its purpose is to make sure it's a real outage. So if it goes longer than 2 seconds, yeah, go. So it'll start the generator set. Once the generator set comes up to speed and frequencies, there's voltage sensors on the utility side and the generator side sensing the voltage. Once it sees that there's generator power available, it switches from this position over into this position, and now we're feeding generator power through the contactor down to the building load. That's how it works. Again, in an open transition scenario. So we talked about one time delay, and that was the time delay start. We didn't want to slam the starter home. The second one is once the generator's running, it's kind of an optional time delay. It's the least critical. We'll give it just a few seconds to run unloaded before we hit it with load. I'll interject to Chad's point earlier. In this situation, this is a non-legally required. It isn't legally required because we've got to be online in 10 seconds for NFPA for legally required systems. So this time delay, that's why I say it's kind of optional. And the only purpose for it is to allow the engine to run a little bit of time before you hit it with a load, to warm up, if you will. So, but we've already got the engine warm for NFPA situations with the jacket heater and stuff, so you shouldn't need that. Anyway, we're running on generator power now. The third time delay that's in all transfer switches is a time delay on retransfer. I'll give you a situation for that too. Hot day, summertime here, extremely warm. Everybody has gone over at some point and turned on their air conditioner, or they've got it set on the thermostat. All the air conditioners are running. Utility fails. Nobody that I have ever talked to has told me, boy, as soon as the power failed, I ran over and turned off my air conditioner. Never happened. When power comes back for the utility, if you think about it, now, even though everybody turned their air conditioners on at different times throughout the day because they were hot, Now the utility has to deal with nobody turned them off. So now the utility, when it comes back online, has to start everybody in the world's air conditioner at the same time. So they're going to see a heck of a spike. Very real situation, and it happens. So you might see the utility come back for a second, and boom, especially if it's a hot day, go right back down again, and that's why. So third time delay for all transfer switches is a time delay on retransfer back to the utility. That is typically set. We set it for about 15 minutes. What that does is it ensures you've got generator power already. We don't need to be flopping back and forth. So it ensures that the utility is really back there and is going to stay on. So then it transfers back to the utility. And the last time delay, the fourth time delay on all transfer switches, is a function of modern technology. Most engines on engine generator sets today are designed with a turbocharger. That turbocharger runs very, very, very hot and very fast. And diesel engines, anytime they're loaded, they're the hottest they're going to be. And if it's a full load, they're going to be very, very hot. And it's directly proportional. The heat of the engine exhaust is directly proportional to the amount of load that's on that engine. So the fourth time delay, we transfer back to the utility. We're going to allow that generator set to run for maybe 10, 15 minutes unloaded. Why? Now we're running cooler exhaust air through the exhaust pipe to help cool the turbocharger down a little bit before it shuts down. All four time delays. Here's what an open transition ASCO transfer switch looks like. Little gray box. Most of them, this is a Series 300, just a cost-effective switch. Basically, 3 parts. You got a little control panel here that's, this is the back side over here on the door. This is the brains, the heart of the control. Got little dip switches in there, you can make settings. And this is the actual contactor in the back of the switch that's actually doing the transferring of the load itself from utility to the generator and back again. All right, that was open transition. Now there's such a thing called a closed transition. And these kind of escalate too, from simple design, more complex design, dollars follow proportionally. So this is a more expensive design than the open transition. And because we're closing actually to the utility at the same time we're on generator, both sources are closed together for just 100 milliseconds. The utility gets a little nervous, so they might require us to put on some super spiffy protective relays. These are typically made by Basler, Schweitzer, manufacturers like that. They're designed to operate very quickly. So they may require that. Each utility is different. They have their own set of interconnection. If you want to be on our grid, this is what you got to do. That kind of thing. This type of switch is not for all types of loads. A very good load that this is for is anything that modern lighting, discharge lighting for warehouses and stuff, that kind of thing. It works pretty cool because there's no blink in the lights and you don't have a restrike time to deal with for that lighting. So that's a real good application. There's no blink in the lights because we're closing both sources together for just a second. This is what it looks like. This is right at the instant of transfer, if you will. We've got utility power coming in. Normally goes through its contactor. This actually has 2 complete sets of, or what I call a pivot style contactor. Let me go back. Here, we look at this. This has got a single pivot in it. It can only be in one of 2 positions, either here or here. And so I call that one pivot point with this dot, if you will. This design has 2 pivot points. Its contactor over here can be open, and this one can be closed. Or in the instance of what's being shown here, both are closed. Or it can have the reverse true, so it's open, or both can be open. But here the utility power comes in under normal situation, feeds the building load. On the transfer, like I said, the generator will close for 100 milliseconds, so we're looking at it right smack in the middle of that instance, and both sources are closed to that load. And immediately afterwards, the utility will open. That's the closed transition. Transition only. A bypass isolation transfer switch. I think this was done in California first. They always come up with the weird stuff.
The wistful one.
This switch utilizes an automatic transfer switch contactor and a manual transfer switch contactor, but there is a reason for it. It's more expensive than conventional switches because it's got 2 contactors. That's pretty simple. But it's used where manual intervention will allow functioning of the emergency system. Case in point, another example to illustrate. Hospital. Doc's got a guy laying on the table. He's got the knife. He's right in the middle of doing his thing, and we're on emergency power. It goes dark. Not good. This switch will allow the manual intervention of switching the switch manually and getting power to the doc in the operating room so he can keep operating. That was basically the heart of why this started. Let's take a look at what it looks like on a 1-line. Under normal circumstances, normal power comes in here, feeds through, comes out to the load. Okay, normal, and this is the since this is the rack out portion, the switch on the bottom is actually the automatic transfer switch. Okay, so normal power will come in here, through there, through the switch, through the normal contacts, and out to the load this way. So all is good. Now, this thing fails, we have to rack it out. All you have left, this is now gone, this lower part here. So all you have left, and we're on generator power. The guy's on the table, the doc's got the knife. So normal is gone, it's dark because the automatic switch is dead. We have to go up and manually close this guy. So now the generator can provide power up through here, through the switch, and out to the table. Manual operation, bypass isolation, big word, but that's it. You've got 2 hole contactors in the switch. That's the reason for it. This is what it looks like. It's a massive beast. This, if you're familiar with draw-out breakers, this is what the bottom looks like. Here's the switching handles. This is the crank that brings the automatic part of the switch out, so you can rack it out and go work on it on the bench or whatever. This is your manual switch control up here. Lots of different ways to switch load. Automatic transfer switch, soft load transfer pair. This is an expensive part. 2 breakers act as a transfer switch. The transfer is transparent to the load, and I'll explain this when I show you the drawing. User-friendly and curtailment programs. And because in a power outage we only have one time that the room goes dark. Because we're connecting to the utility all the time, or for a long time, it requires the utility approval and protective relays. Again, you're going to be on our grid, this is what you need. And it's the most expensive design. Basically what it looks like, utility, generator power, both electrically operated draw breakers shown here, connect to a common bus. They're together. We're synchronized through controls, synchronizing controls on the generator. So we're at one with the utility, supplying building load. Typically what's done, a good instance in a power failure, it's going to go dark, can't help it. So utility's gone. We open that breaker, we start the generator, and we run the load. Just normal operation. When the utility comes back, because it's electrically operated, we have controls that are going to say, well, no, you can't close. We'll synchronize the generator to the utility. And when they're in sync, we close the utility breaker, load ramps off the generator back onto the utility electronically through a loading control is what they call it. And then we open the generator breaker and it times down. The advantage again is the load doesn't know anything happened after we're on the transfer back. I mean, we put Granite's meters on the output to see what the interruption looked like, and it didn't see anything. So very, very, that's why they call it a soft load. Load doesn't know anything happened. That's what it looks like. This is a local manufacturer that built it, and we have a utility main here and a generator main here. This group right here is the selective, it's the protective relay package. That particular one is a Schweitzer. So that's what they look like. And put them outside. This is, you'll see them sitting right next to the transformer and the cabinetry. This one again is at that Super Target store, so I threw this picture in. All right, that was your very quick exposure to transfer switches. Any questions there before we move on?
Just one observation, Jerry, just for you guys, because Jerry talked about two types of transfer switches. The transfer switch that we're going to be using is not the closed transition, open transition in this project. It's auto open transition, the first type. The last type, the soft start that Jerry talked about, we're going to be using it for next project. Next project with Michelle Cooley, we're going to have a 4,000 amp switch here, where we're going to have power circuit breaker, we're going to do parallel with the grid. So the last type, the soft transition, just keep it in your mind for next project. So just to check that. Any question for Jerry yet?
Back. No, no. Let's go back to that one line here. They can't. They can't be operating at the same time, and the reason for that is let's take a power outage again, or an exercise period. All generator sets are going to be exercised from time to time. We've got no power failure. Both sources are available, right? We start the generator set. In that instance, we've got a normal situation. Utility is on. So this breaker is closed. We're supplying load, okay, to the building. But we don't want to have this breaker closed because that generator's got to start up and come up to speeds. So it's not ready yet. So we are monitoring on the utility over here. We start the generator set. This breaker's open. Again, both of these are electric draw out and electrically operated. And we aren't going to give a close signal to that breaker until the synchronizer part of the paralleling gear has got the voltage amplitude matched. We're at 480 here. We want to be 480 here, okay? And we want to have the frequency matched. We can't have any phase shift between the two. Let's draw that. Can I erase this?
Yeah, there is an eraser. You can actually draw right on the screen.
On the screen? Okay, we'll do that. You told me I could, but I'm a little nervous.
Yeah, there you go.
This one's broken. So we want to have, takes a while. The main thing is the frequency. There's the utility. Here's the generator. So once it's up and running at speed, we've got the voltage pretty close, so we can get that tweaked, and the voltage regulator will take care of that. But we've got maybe 90 degrees here between the utility and the generator. If we were to close that breaker, here's our result. So we've got a spike there. We can't deal with that. So that's why we have to have a synchronizer circuit to take care of that. That puts the two in sync together. And once we have voltage and frequency matched, totally in sync, it looks like one waveform on a scope, then we close it. Same thing coming back. In the instance where the power failed, the utility was gone, right? So the first thing the paralleling gear does is they send a signal over here and they pop this dude open. So now that breaker's open, we're running on generator power to the building load. So utility comes back. Again, the controls are going to say, you're not closing. We'll get the generator. The only one we can control is the generator. So we have to go back over to the generator, even though it's running the load, and tweak it a little bit into syncing, especially the frequency part. Voltage is easier, but the frequency, once it's in and we don't have a resulting phase angle that's going to give us a spike, then we close the utility back. So both cases, we're tweaking the generator. We can't mess with the utility.
I have no control over
None. Okay. Good point. Good question. Any other questions? Did I answer it for you?
I have another question.
Okay, go ahead.
More of like that 10-second rule.
Uh-huh.
That's like kind of generic rule. If there's no inputs, like let's say a tree falls on the branch.
Okay.
You can take the power.
Yep.
There's no system that will like grab the power without it. Because how it's like that with generator. There's like battery.
Good question. Good question. Let's go back. Well, let me draw it again. Let's take a simple switch just to illustrate your point. And again, this is the one you're going to use for your first project. Here's load. Here's what's happening. That's a breaker. When the utility fails, tree falls on the line, to your point, okay? Utility is gone here. There are voltage sensors on both the utility side and the generator side. So what I'm telling you is once the voltage sensors here see it, you are correct. There's batteries that are running the control.
Does that come with the generator? Or is that like the secondary? Yes.
It can be either, but typically it's just the generator battery. This is a pretty simple system. So once it sees it here, and they can even use a relay that's on emergency and there's no batteries. Okay, the relay drops out and gives it's a normally open set and it closes. Okay. That tells the generator set to start. Okay. Once the generator's up to speed and frequency, the sensors here again see it and say, bring me the power. So it switches. And to that point, since you're thinking like that, you might also need to remember that any transfer switch has to operate off the power of the source that it's transferring to. Make sense? Answer your question? Anybody else?
So basically, if I summarize a little bit here, Jerry, is when you lose power, the generator has a battery in it. The auto transfer switch will use the battery of the generator, right? Because we're going to the generator right now. to sense that there's lots
Yeah,
of
maybe
power.
the battery thing was not a good illustration. That's why I went back to the relay concept. There's something in the sensor there that will close a set of contacts, which is going to operate the generator battery to start it.
So you'll have a normally open contact that as long as we have power from the utility, that contact will be open. The minute that we lose power, like you said, it's closed to start the signal for the generator.
Gives the go signal.
Good
Okay.
point.
Good question. Anybody else? All right. Types of loads. We've talked all about the generator sets and switching power and transfer switches and so on. Let's talk about the different types of loads that are out there. And you guys probably know more about this than I do. So basically, how come my...
You good?
Okay,
Good for that?
I can use this. Nonlinear loads. This is the nonlinear loads. I make a statement here. It says nonlinear loads need diesel engines. That's a personal opinion. It's pulled right out of experience. So what happens? I'm going to draw another picture. I'm getting to like this thing, Sam.
You can,
Okay.
you have different colors though. You can do.
I like colors. If we look at a nonlinear load, you probably know that there's electronic devices and they're SCRs primarily that are actually spiking this waveform. If we were to look at it on a scope, we'd see these little notches all over the place. And that's from those SCRs firing on electronics. That's a bad thing for gas engines. And this is only by personal experience. Diesels react better to loads. I had a situation where I had a natural gas engine and an SCR load, and gas engines and diesel engines react differently to loads. And I could not get, these signals sometimes get fed back from the output of the generator, the output waveform. They have what they call a shunt excited set. They'll actually couple a portion back to the voltage regulator. So what this circuit is for is under normal circumstances without the notches, if it sees a drop in amplitude or voltage, that coupling back to the voltage regulator says, oh, we need more excitation. So it feeds more current into the exciter, and when that happens, we get the voltage back. Okay, part of the automatic voltage regulation. Well, now we'll put the notches back in. And natural gas sets, for whatever reason, if they're shunt excited, that gets coupled back to that regulator, and it sees these notches as zero crossings, and the thing just goes nuts. This problem has been pretty much fixed in the industry over time, and it was primarily due to the SCRs when UPSs came up. Uninterruptible power, because we're doing exactly that, and it notches the heck out of the way. So that's an old thing, but that's the nonlinear load issue, and you see it in VFD drives and that kind of thing too. They do run better on diesels, but a lot of natural gases. There's been other things to come along to help fix that issue. Nonlinear loads do need special consideration in sizing. That's because of neutral currents that are generated by UPS systems. Examples: UPS, battery charger, VFDs, T8 ballasts and lighting are nonlinear. They can be offset with other loads. One of the things I learned when I ran into that natural gas problem was if you put dumb loads on with the nonlinear loads, you can help damp that notching effect out. Let's talk a little bit about a UPS system and what it actually is made up of. We know it's an uninterruptible power system. It's used to maintain power to a critical load, so it never sees the outage, and we'll go over that. These are typically at a data center or something like that, or at the IT department in any company that's got, you know, it's your main computer system for your company. So any of those instances. How they work. Under normal circumstances, they're basically made up of three parts: a battery charger, batteries, and an inverter. The battery charger changes AC to DC, and we're going to charge these batteries with it, which are tied to the middle section, which is the battery. And then take that DC to an inverter and change it back into AC here. Well, why go through the bother? Well, if the utility out here fails, this is gone. The battery charger quits working. Batteries aren't being charged, but we're still connected. These batteries are still connected to the inverter, so the DC is still being changed to AC, so we still have our output here, and we're still powering our critical load. Uninterrupted power. Hopefully what's going to happen, and we'll see it, I've got a one-line drawing that I'll show you in a little while, that this will never see an outage through the outage.
Just one little thing, Jerry. We will be using a UPS, guys, next project. We have data centers for the industrial project that you're going to be designing exactly the same thing. Just FYI.
Okay. Other motor loads. We've got air conditioners or rooftop units, chillers, elevators, and in all the stairwells and stuff, we're going to see pressurization and exhaust fans. Maybe in the water system, we'll see circulating pumps, and we're going to see a fire pump. Other types of loads are out there for motors. Lighting can be incandescent, fluorescent, discharge. We talked a little bit about discharge for warehouses and stuff. Outside lighting too. Okay. This might be very good for the project here, by the way I've got this set up. We might look at a partial building for our first scenario, and maybe the entire building for their second industrial project. Partial building design. Here's the one line I was telling you about. Power flows from utility power through our entrance rated fuse disconnect into our main distribution panel, through our automatic transfer switch, to our emergency distribution panel, which runs over to a UPS, which feeds critical load over here. We might have a spare in our emergency panel. The other things that we don't want to put on the UPS, obviously we don't need to run the air conditioning on the UPS or the emergency lighting. So those are kept on the emergency distribution only. The supercritical load comes in utility through here, through the switch, through the UPS to that critical load. If the power fails here, so utility's gone, this goes dark, this goes dark. Generator set starts because the voltage sensors here saw it. Go generator. Generator comes up to speed and frequencies. Voltage sensors here see it. Switch transfers from this position to this position. Generator supplying load through the emergency distribution panel, through the UPS to the critical load. This wave never went away because generator started and transferred within 10 seconds. Charger was only down for 10 seconds, and hopefully our batteries lasted more than 10 seconds. Questions? Important concept. You guys are going to be facing this, designing this a little later. The entire building design. Sometimes it just makes sense. We don't want to do a lot of wiring inside the building. Let's just do it all outside. In the case of that super target, that's exactly what we did. There's nothing going on the inside. We did it all outside. We put on, again, this is a paralleling piece of gear. It actually sat outside in a heated enclosure. Generator set was out there. Building load is here. Only one entrance point into the building. It worked out really good. Again, the soft load switches, like we discussed before. Utility goes out here. First thing the controls in this gear does is open this utility main. A little bit of a review here. Generator set starts, comes up to speed and frequency, closes the breaker, doesn't care because the utility's gone. It just shuts the breaker when it's ready, and it provides power back to the building. Utility power comes back, transformer heats, this breaker is still open. Utility again is available, so the controls in the paralleling gear start tweaking the generator back into sync, closes the utility main now. Both breakers are closed, supplying load. Load ramps off the generator set, opens the generator breaker, times down for cool down, and we're good to go. All things as they were before. Other considerations in design of emergency power systems. UL 2200, I'm not going to spend a lot of time here. It was established in '98, that's a long time ago. Pertains mainly to the manufacturers of generator sets, so we have to manufacture them a certain way, and these are some of the things that they address. It only applies to systems that are 480 and below, not medium voltage or high voltage systems. Open or closed, enclosed units, it applies to all of those. Any fuel. And it primarily involves changes to block heaters, battery boots, grounding straps on the alternator. Noise is another consideration. EPA getting their hooks into everything that we do. Many municipalities now have got noise ordinances. They're becoming very, very common, but they usually put them on the website so you can see them. One thing about the noise, I've told you before, noise travels in a straight line. Typically, noise ordinances are never enforced unless there's a complaint. So, but can you take the chance? Noise can be attenuated in several ways, and it's not going to go away. I guarantee you. I like throwing these in anytime I talk to, especially students, people that are new to noise. It may be required by code, obviously it is. The standard for the industry, for whatever reason, they picked this noise and they quantify it in a certain dBA level. A being decibels attenuated to the, be similar to what the human ear can hear. That's dBA. And it's a certain level at 23 feet. And one thing that I always tell engineers when you write your specifications, yeah, give me the level that you want, the distance that we have to be at, but say at full load, because there's a difference between no load operation of the generator and full load. It gets a little noisier when you put load on it. So I tell engineers, cover your butt, make sure you put full load in your specifications. So it's got to be quantified, you got to tell it what the distance and under full load. Reducing noise costs money. Question?
Average, or is that from like site dictating, like neighbors' houses that are already that distance?
I have no clue. Some code guy came up with that. They said, well, we're going to standardize. This is the distance we're going to talk about. 23 feet, 7 meters, whatever you want to call it. That's what we're going with. It was somebody on a code committee. They had to come up with a standard. So that was it. That's the distance they picked. And we're going to talk about some rules of thumb. Because we do have 23 feet, that's a figure we can work with. Because if you think about it, if we get too close to the generator set, these rules I'm going to give you, these rules of thumb wouldn't make sense. But 23 feet we can work with. Doubling the distance from the source, sound is reduced by 6 dBA. So if we started at 23 feet, which is about 25 feet, we will have, with 80 dBA, 50 feet away, we double the distance, we drop it 6 dBA, it's going to be 74. That works pretty good. And another one is 2 equal sound sources. Two generators operating at 80 will have a combined noise level of 83. It increases 2 equal sound sources, increase the overall by 3 dBA.
It doesn't double.
It does not double. It's not linear. To the human ear, twice the loudness is a 10 dBA increase. 80 dBA sounds twice as loud as 70. I don't know who came up with that one, but any smart guys. Here's what the decibel equivalents look like. I like down in the bottom, thinking is 0. Falling feather is 0. Mosquito in flight is 10. Computer might be 10. Frogs croaking is 60. This was one from my Cummins days. I liked it though. Just a fun thing to look at. Motorcycles are getting up there. Subway in a tunnel. Car horn is 100. Jet engine is 130. I think Rock Band was in there someplace. Oh, it's on this one. There's another one that I had. This one was the Cummins one. Rock music was up there between 110 and 120. So don't crank up your iPhones or your iPods or whatever. All right. Other considerations that you need. This one has made me very old, and I'm getting older. Emission standards. They continue to grow. We're dealing with emissions escalating now for generator sets as well. You guys, as you get into generator sets, you're going to find that some of the costs you were concerned about, what's the most economical earlier. Some of these costs are going to go totally nuts. We're going to double, triple the costs of generator sets to address this issue. One of the primary things for new engines that we're dealing with today is we're going to a Tier 4 engine by the year 2015. What that means is we've been in a progress so far. A lot of engines are at Tier 3 now. We do have some that are at Tier 4 already, but they're little engines. They're cleaning up the exhaust. Primarily, the concern that you see is this guy right down here in the bottom is, with my pointer's gone, there it is NOx. And the way we clean that up is with a what we call an SCR. It's not the SCR you're thinking of. It's selective catalytic reduction. And what that does is we introduce urea into the exhaust stream, and it becomes ammonia. It wipes out a lot of the NOx, and we can reduce it by up to 90%, which is what the EPA wants. But it's another commodity that this generator set, this diesel generator set, is going to consume. So we've got more consumption. In addition to the diesel fuel, now we're going to be consuming urea in approximately a 1-to-7 ratio, urea to diesel. So it's making life hard for us. What I'm throwing at you today is a little bit about some of the current codes. ISO 858 or 8528-1. I'm not going to spend a lot of time on the regulation part of this. Primary things I'm concerned with as a sales guy is the emergency standby power and prime power primarily. The important thing, in 2011, the EPA redefined what emergency power is. They said anything that operates only when the power fails, we're going to call emergency. Everything else is non-emergency. And this is primarily diesel. CI is compression ignition in this slide. So that divides us into two markets, emergency and non-emergency. Non-emergency being anything else. An example, peak shaving utility programs. There were programs out there that benefit customers. Electrical utilities like XL Energy said, hey, got a program for you. You're a big customer, got your factory out here. How about you've got a generator system already? How about we make a deal? On a hot day when I need power, and I won't want to buy it from Canada, how about we send you a signal, or we call you and tell you, run your generator sets. For that privilege, if you do that for us and transfer over onto generator, we'll reduce your power bill 40% all year long. Pretty good deal. Some of them were up to 40. XL is a bad example. They were down around 10 or 15%. But still, if they needed backup power anyway, here's a utility that was going to subsidize them getting backup power. That's a pretty good deal. It was a win-win-win. Customer won because he got a lower power bill all year long. Utility won because they didn't have to buy more expensive power from Canada. I won because I got to sell the stuff. So everybody wins. The government comes in and they mess it up. There I go again. Oh, I'm on YouTube, aren't I? Bad. Just kidding. So that's the situation we've grown into. So we've got constraints now put on us. And this definition that they did in 2011 applies in another way. They're saying, okay, emergency generators, you're okay just the way you're at. You know, you've got a tier engine on you right now. You can still operate on the tier engine that you have now. No problem. Non-emergency, the peak shaving program I just alluded to, now has to have a different set of emissions requirements. This one, emergency, here's their definition. I told you they redefined it in red here. If you want to read that, you can. But basically it says anything that operates when the normal power fails. So that's the definition. May be operated for the purpose of maintenance, checks, testing. It's limited to 100 hours a year for the testing part. That's the exerciser that we do, automatic exercising of the equipment. But again, there's no time limit on the use of the emergency generators in true emergencies. When the power fails, I don't care if it fails hundreds of times, you still aren't required to do anything else. You've got what you need. No problem. It's just as it is today. Okay, and that, as far as our products are concerned, we're there right now, so no difference. Here's what it looks like. This is the sickness that we've been going through with the tiers as we gradually pare these engines down and clean them up. Here's the timelines that we're dealing with. This is emergency, remember. So we're good on anything that we need. And the colors are just the different tier levels. Big engines are only on tier, well, it's 2011 now. Well, they're up to tier 2 right now. So tier 2 is the earliest tier. The green is tier 3. These little guys down here are tier 4. We're in those right now, but that's for emergency. This is down in the 30 kilowatt range here, and our sets are there already. So everything you see here, we're already doing. No problem. Non-emergency. And to my point, I highlighted it in red. This is for the engineers that I deal with. Stationary compression ignitions used to supply power to an electric grid, or that supply power as part of a financial arrangement. The deal. Hey, we'll give you this if you do this for us. It's a financial arrangement with another entity. the utility, are not considered to be emergency. I mean, they shot this program right between the eyes. So they got us. Okay, so if we want to continue, customer looks at me and says, Jerry, I want to be in this program. It's a good deal. What do I do? The EPA says that we've got to get these existing units now up to a new generator. It's got to be the next tier level. This is the chart for non-emergency. You can see that blue, tier 4I, we're there right now, with the exception of this one little KW node, which I have no clue why that got the exception until 217. But everything here is tier 4. That happened as of 2011. The bigger units are right here on this line. So 2011, that's the effect this program had. So if the customer wants to participate in this program to get savings, he has to spend a lot more money up front. Bad deal in my book. That's a personal opinion. But you need to be aware of that. There are special emissions criteria in effect today. What will these changes require? And this is of me as an engine supplier. It's going to have the SCR technology I told you about to lower the NOx. Particulate filter now, which is out here. This is the urea dosing tank that gets injected in there, and the output is going to be water and nitrogen. There's also a thing called a low particulate emission that's really not shown here. This is a catalytic. This is a oxidation catalyst. SCR, we're going to reduce particulate matter as well as oxidate and get the CO down through an oxidation catalyst. And it's going to bring emission levels down probably about 99%. Just a quickie little slide on the process if you're interested. The nuts and bolts, as I said, they've made it a little more complex. All of the componentry you see here has to do with getting urea in the right amounts to a varying load. So there's computer control, a lot of parts and pieces. I have totally backed off. Let me back up. The EPA is requiring that you either have a certified engine today, which no manufacturers do, or if that's not possible, they say we'll accept an EPA compliant engine. Well, what that is an aftermarket supplier, and there's several of them out there that will sell you components. But these components have to be assembled, and you can see what they look like here. It's pretty complicated. They have to be plumbed. They have to be programmed because there's computer control in there. And that too, in addition to the expensive components, we have expensive programming, assembly. So we have a huge assembly cost, which is going to vary. I'm not interested. I want a factory certified package. Why? Because it's a complete package from the factory. They will say, we will meet the emissions. Now think, if I do this, I tell this aftermarket guy, you can come in, we'll put the stuff, make it work. Who's guaranteeing the emissions? The EPA is looking at me. I don't like that. I'm on the hook to make sure that this thing produces. I would rather that be on the engine manufacturer. And I just see litigation all over the place. So it's a bad deal. We're in a bad time right now for people that want to be in these programs. All right, installation on the SCRs. There's a lot of componentry there. This shows the tube that the urea gets injected into, and storage is an issue, especially here in Minnesota. They use a solution, 32.5% solution, which starts to crystallize at about 15 degrees Fahrenheit. So what does that mean? We got to warm it. So lots of issues. Here's what they look like. They're clean, but they're kind of gaudy. A little bit about after treating. Here's the component costs, installed costs, lots of dollars. We don't need to go into all of that. This is primarily for the engineers, but I wanted to throw it in there to show you. Any questions? Anything I covered? I covered a lot of stuff in a small amount of time. We're going to talk about more. Anything you have a question on anything that I've covered so far? We're going to take a break here in a minute. We're going to have the second session where we're going to go through some sizing. Okay.
Short session, guys. Should we have 5 minutes break? And then I know you want to go to lunch. We'll go at lunch after that. So we go 5 minutes.
The next session will be relatively short, so you'll get to lunch pretty quick.
Awesome. We're good. Okay. All right, guys. Jerry's going to walk you quick. I know I walked you through comments generating software. And maybe Jerry will say a few things about his history with the software. He hasn't used it for a while, so he has to readjust it, recalibrate it. What I asked Jerry to do in particular is to talk about the specification for the engine, the height and the temperature and the voltage depth and all this stuff. Because you guys know how to do the steps. He's going to do a few steps for you, a few loads. Just go a little bit deeper into the meaning of the loads and the meaning of the engine when we derate based on elevation and so forth. So,
okay. Start with, we'll just create a new project. And let's see. Yeah, we don't need to give it a name really. We'll just put some loads in. Start with the first step here. Go back to loads. We'll pick a load, a lighting load first. We'll give our project about 10 kW worth of lights. Call it single phase, fluorescent. Next, finish. We've got our lighting load in there. We'll take a motor load. Let's pick a big motor, maybe a chiller, and we'll call it a chiller. Bigger building we're working on now, and it's got actually got a 75 horse motor on it. It's a variable frequency drive. 3-phase, it's 208. Good. Next. Oops. So we'll finish that out. We've got a VFD on our chiller. Very common application, actually. What else? UPS. Got a UPS. UPSs are rated in kVA. Why, I don't know, but they are. So we have a 30 kVA in the IT department, and it's a pretty nice one. It's got a 12-pulse inverter, so it's pretty spiffy. And everything there looks good.
and I told them, Jerry, to keep the default unless you know otherwise. When we do the loads, you've been doing the same thing. You keep the default in terms of power factor and so forth, unless you know otherwise.
Yes. Very safe way.
Yeah.
The defaults will keep you out of trouble, because if you go too lightly loaded, you could undersize things, which is a bad thing. Air conditioning loads. Let's try one of those. We'll call this a rooftop unit. This is RTU 1. And that's only a 5-ton. It's not too bad. This is just covering the IT room. It's not a variable frequency. It's over across the line. Okay. NEMA code letter is H. Good. Everything is good. So, and then we got our fire pump. It's actually a 50-horse fire pump. Something on fire pumps, guys. It's important to know. The main thing about a fire pump is 15% is the maximum amount of voltage dip. Most current sizing programs know that, and they will take care of that for you. The other thing is, in addition to the 15% voltage dip limit, is you can't really put any voltage reduction and take that into consideration. For instance, an auto transformer. You can have it on the thing, but you have to size it as if it's starting across the line. Okay? Couple of quirks with fire pumps. You got to be careful, because they want them to be supplied with load, and the breakers that they put on, you know, they're really goofy on how they size them. They want them to burn up. Protection is there as a disconnect, but because it's an extreme fire situation, they don't want any chance of that breaker tripping. Many engineers will tell you just put a magnetic only breaker on, so it's basically just a disconnect. It has no thermal portion to it. So caution there. Fire pumps are a weird load and one that need extra attention. So we'll go across the line with that. All right, that's enough. Let's throw in a few steps. And we'll sprinkle our loads across there. Lighting load, we'll drop that into step 1. Yep. UPS is typically going to want to be on pretty quick, so we'll put that in step 1. After we get the current stuff running, we'll throw our chiller on so our water keeps going good. And we probably have some fans and stuff that we put on too. Let's see, we got that. We got our rooftop unit we throw in next. And then finally our fire pump. No, it's kind of random here. Fire pump I usually put last. When I do these though, however, I always want to have it in my head. What's the worst case that could happen? That's a great question. We want to set it up to where our biggest load might be starting the last. Everything else is on and running, and we put the biggest load on last. Why? If it's going to take a lot to start that biggest load, and our generator's picked because it is last, we got it covered, right? And after we get it covered, we might see what our set is after we get all of this done. And we want, what I do, and there's no magic to it, but I pick a 70% generator loading, because all of the loads that we plug in there, if we take an average day when the power fails, maybe all these things aren't running. But we've sized it so it is all running. And if we've sized it with the biggest load last, and we're still starting and running, we've done a good job. And we'll go back and look at the very end and see, once everything's up and running, I like to size it at around 70% of the generator set's capabilities. That does a couple of things. Customers, you ask them up front, are you planning on expansion? Like you mentioned earlier, we're going to put 50% more on this building later. We want to allow for that on day one, not when we're getting ready to do the expansion, which might be a year or two later. So if we've covered it up front, we've done a good job of engineering. Good question. Okay, this one has the notes about the 15% voltage shift. That's very good. So we've covered that. We'll go up and do a size. There we go. Comes up with a 230 kilowatt set. And Chad wanted me to talk a little bit about this. Let's talk a little bit about the parameters that we're looking at right now. The load requirements, and this is set up in the defaults. Where was that?
You have to go back to gen size. The icon in the upper left corner.
Here?
Yep.
Okay.
And then project.
And then projects, okay. In the defaults,
Edit.
Edit. Default preferences. In this one, we set it up right here. And you notice on the selection that we just did when it calculated, it said voltage dip 35. This is where it's coming to get that. Maybe we don't want to go to 25. Maybe we want to make that, or 35. Maybe we want to go to 25. Let's change it here in the defaults. And then we'll reselect it. We'll recalculate. The rest of the stuff looks pretty good. Maybe you're working out of your territory here. You know, you're engineering in this one place, but the project's in Denver or someplace. Here's a place to, and that's a big consideration, especially in emergency standby power. What's the altitude there? Because there's D rates for all the generator sets that we have. And it's very specific to not only altitude, but temperature. So you plug those values into your defaults as well. Each one of these that you bring up can be edited in this way. So you can tailor every sizing that you do to the location it's going. Very important consideration. Okay, so we got what we wanted here, our altitude. Oh, shoot. We're at 1,000 feet here. So we'll plug that in, and it calculates the meters. Thank goodness. Okay. Sound attenuation. Yeah, we'll leave that in. Fuel. Okay, good. So there's our parameters. Let's recalculate. We had 230 before. Let's see if it's still, yeah, it's still fixed at 230. Okay. Oh, it's still saying 35. You got to do that up front, I think.
I think we did it for the default. We had to do it for the project too.
Ah, okay, okay.
So if you do, we have to go back a little bit one more time.
Over here?
Yep.
Okay,
Click on the new project
new project.
and then go projects.
Oh, right here.
Up the top, the upper.
Huh?
Where we were, the upper.
Oh,
Yep.
yeah, I can't hear.
Edit. Yeah, they have the default. And right, I mean, selected project. Now we're dealing with that particular.
Ah,
Yeah, they
very
have
good.
one for default and one for
okay.
parameters.
And we would say our,
The second.
and then we'll go over here to parameters. And here's where we can go 25%. Let's do that. All right. I have not worked with this for a
I
while.
made the same mistake.
Ah.
2 days ago. That's why I'm blaming. We
Very-
just went through the exercise a little bit.
Very good. Now we're showing 25%. Now we'll recalculate. And it still picks a
Yeah.
230, so we're good. Let's take a look at some of the other things that are down here on the bottom. And surge requirements. Okay. Oh, just randomly picking these loads. Look where the rated capacity came out. I said around 70%. So not a bad choice. So it fits with what I want to do. Then you may ask your customer too, or if you know of the expansion of the facility, allow extra for that. And what you would do is what's that expansion going to have in it? Are there any particular pieces of equipment that we know are going to be added then to mirror what we've already got? Make sure you factor all of those kinds of things in and plug them into your model here. Make sense? If it's just going to be additional seating for employees and lighting, it's not a big deal. But if it's machinery, if it's part of a factory that's going to be expanding, it's a big deal. And does that area have to be cooled or have compressed air in it? All of those considerations. That's going to mean a compressor. It's going to mean a chiller, maybe a rooftop unit, things like that. Okay. I'm over here. Here was the original. We're moving over to load running and surge requirements. Remember I talked about motor loads requiring a lot when they start. Let's take a look at that. Do we have we got a running KVA, running KW. Do we have starting? Cumulative step KVA, 428. max step kVA 295 and step 4. So we're calculating that. We're looking at all the considerations of motors starting, and it's telling you in what step we're doing that. So if we went back and looked at the steps, we could say, oh, okay, it was when we did this. So a lot of good information is included here, including what we want to see on the percentage rated capacity. Then finally out here it tells you the particulars about the set. And this is important because we know what engine it has on it. It's got the LTA 10, I should say. It's got an HC4D newage alternator on it. It's got a broad range alternator. It's reconnectable. Here it's telling you altitude considerations, what it's good for, even though we don't have durations considered so much on this site. It tells you what it is on this particular generator set. So all of that is there.
Engine, is this telling the type of generator used for? I don't know.
This is very specific. This is exact the engine and the alternator, or the generator end. The generator over here. Okay. It picked this model up here. Okay, this 230 DFAB, which has this engine and this generator. Okay, very specific.
And I told him, Jerry, that when we have an engine generator set, guys, and that's from you, I learned it over the years, is engine generator set is 3 distinct pieces. The engine piece and the alternator piece and the radiator piece. So this is will give you down there, it's giving you the alternator where you generate the power and the engine where you drive, burn the fuel to get you the movement that will be generated. So,
Correct.
so you have 2 things.
And something I was talking to someone about during the break. It's important to remember. You see 2 values listed all the time. Whoops. This thing.
After what, you have to put the eraser down there.
Oh.
The rules of the game.
Oh, that's what got me before. You have this, you can't write. Oh.
That's interlocking.
Uh-oh.
Mechanical interlocking.
Oh, I'm getting too old for this. We see KW and KVA on generator sets. Kind of an important consideration and kind of a thing that I want to tie together. Think about the KVA, since we were just talking about this and the components on the bottom. That's coming out of the alternator. Okay? Electricity, that's coming out of the alternator end. KW, that's power. Real power. That equates to horsepower, which is coming out of the engine. That's a good way to think about it.
You know, you,
Hey, that's on the computer now, too.
Yeah.
That's pretty cool.
yeah, you might have to. No, you can leave it. Just take a second here. Picture out of here. Picture of it. And so I've got a picture of what you said.
Technology is great.
Sounds handy.
Even old guys can learn. Okay, that was kind of quick, but it's gone through the sizing. Is there anything else that you'd like to talk about?
Any question, guys, about that software? And if one little thing, Jerry, how do the engineers, you guys work for engineering firms and electrical contractors, how should they use this software? I mean, what do they give to you as a generator owner? Or the people who sell the generator, do they give you that report? Do the, you know, the interface between them being designers in the field, engineering firms, and you as a seller of a generator? Like if I want to buy this generator, what's the best way? I ran the analysis. Then from there, I just go contact you. Here's what I did.
Typically, what an engineer is going to do, that's a good question, because it comes down to how is the engineering community fit in to the overall. there's a couple of different ways. I might be the guy that comes to you as an engineer and says, hey, you know, I got this customer. He's my buddy Bob, and he's going to build a building. I don't know a farkle about buildings, but he knows I'm a generator guy, and he wants to buy the generator from me. Let's have you go ahead, size it up. I'll let you do that part, but I want you to design the building as well. So I'm hiring the engineer. That actually happens a lot these days. They call it design-build projects, and owners will go direct to engineers, or they'll go direct to contractors that they know. That's one mode of operation. So to Chad's point, that could work that way. And I'm coming to you. I'll have you size it, and I'll check you because that's the part I know.
Yeah.
But then he'll include that with the rest of the building. Okay? And then we'll go to the owner and say, here's what we got. Sign on the line. The most common way is the bid and spec market. And there used to be a guy, Randy, that used to be here too for a while. Randy Jacobs. He worked for a consulting firm. And what they typically do is architects will be approached by an owner. Okay, this is bid and spec stuff now. The owner says, I want to build a building. Here's what I want. Here's the property I've got. I don't want to be in trouble with any codes and everything. You cover my butt, design the building, make sure I meet all the codes for building and everything. Okay, so he takes on the project as an architect. The architect will then move to an engineering firm. Might be a Mashad Cooley. He calls Guy Hurd, and Guy says, oh yeah, I can do this. So he'll do the electrical part of the building. Guy's got another partner in the building there that does mechanical engineering. They work as a team, and they put all the componentry together, structural, civil, everything for that particular project for the engineer. They develop a specification. When they get to the generator part, this is the program they dig out. They say, okay, here's the size generator we need. Now we're going to produce a specification. And that's, I think, is that here?
Yeah.
They can do that. We're just going to look at the size right now. But when the specification is produced, it'll describe everything, all of the stuff that's on the bottom, the alternator, the engine, all of that stuff will go into a specification. And that goes into a part of a book. Some of you may know this. And it's a design book specification for the project. Also the drawings. Once the site is developed, we know what it is. They might have an aerial view of the roads that are in the area. The actual structure of the building itself will have architectural drawings, civil drawings. They'll have mechanical drawings for the plumbing in the building. They'll have electrical drawings for everything else in the building. Specification and plans at that point. They pick a date. The owner has told the architect, I need to be done with this building by the end of next year. So all of the timelines are put in place. Specification comes out, and it goes to a builder's exchange. There's one not too far from here that I'm going to after we're done here. And the plans and specs line there, all the contractors. Once it hits there, it's what they call on the street. This is specification and spec and bid market, they call it. Once it's on the street, there is a bid date assigned. You have to have all your pricing in to the whoever. The contractors have to have their price to the general, blah, 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 by this date, and to the owner. It might be a public bid, in which case it might be opened at City Hall publicly, and everybody can hear who won the job. But that's the other mode of operation. That's what competitive bidding is. That's the process. Any other questions?
Any questions, guys, for Jerry? If you have, will you guys work as you work on your projects? If you have any questions, Jerry is there. He has his business card. You can call him at any time to help you size the generator, specify the generator. You guys help starting the generators too, and it's not just putting a gen there. Yeah, you guys will help with a lot of other things, you know. Being consulting engineers, guys, we don't know, a lot of consulting engineers, they don't know how to operate the generator. There's a lot of things involved in having a gen, on site and making sure it works, not just specified there. So this is where Jerry and the team come to help you have a generator sized right, run for the coming 25, 30 years or so. Hopefully.
Yeah.
Any question, guys? For Jerry and the team? All right, thank you. I appreciate it.
You bet.
All right. See you.